We'll start. Good morning, everyone, and welcome to the third lecture of this VSLA course. Um, we'll do a quick recap of what we have done in the past two lectures. So first thing was that we motivated why we need something like a vector space as such, right? And then we saw something called as abelian groups and fields, which are the basis of defining vector spaces and the associated concepts, right? And then we saw how to define a vector space in the first place, right? It's basically the a set with some operations defined on it. For example, we have the vector addition operation and scalar multiplication operation, and and then we saw what are some examples of vector spaces. This homework was a bit I had given that let's try this problem. So we'll try it right now, and then we'll move forward with the next concepts. All right. So first thing is, so here if you see, we have this R on Rn. We're defining two operations, right? It is alpha, beta, and C dot alpha. Uh, and they're saying that is Rn with this plus and dot a vector space or not? And they're asking mainly which axioms get satisfied. Okay. If all get satisfied, it's a vector space. Otherwise it isn't, right? Okay. So alpha and beta, right, are basically tuples of real numbers, right? Tuples of real numbers. Okay. um, the plus circle operation, which is your vector addition operation is this plus circle thing, and then you have it alpha minus beta, right? So it's defined as alpha minus beta, and C alpha is minus C into alpha, your usual operation on the tuples of real numbers, right, which is your vectors in real numbers. So closure property, if you think about it, so closure is basically if I do this operation, that is alpha plus circle beta, which basically is nothing but alpha minus beta, it'll still be a tuple of real numbers, right? So closure is fine. Then coming to commutative tells that alpha plus circle beta should be equal to beta plus circle alpha, which implies that alpha minus beta should be equal to beta minus alpha for all alpha beta, right? Which is not true, right? So hence commutative is not satisfied. Let's talk about associative. It says that if I do something like this, right, this should be equal to alpha plus circle beta circle, let's say some gamma. Okay. So what would this correspond to, right? This would mean that alpha minus beta plus circle gamma should be equal to alpha plus circle this vector, which is beta minus gamma, right? Which implies that, so these are two vectors, right? This is one vector, this is the second vector. So alpha minus beta minus gamma should be equal to alpha minus of beta minus gamma, right? Which means alpha minus beta minus gamma should be equal to alpha minus beta plus gamma, which is not always true for all alpha beta gamma, right? So hence even the associative property is not satisfied. Let's talk about identity. Identity tells you that if I let's say some element E is there, alpha plus circle E should be equal to alpha, right? Which means alpha minus E should be equal to alpha, which means E has to be the zero vector, right? Which is basically the tuple of all zero numbers, n such zeros. That is the element of identity here, right? So that is fine. The thing is, we generally talk about something called as right identity. Okay. So the thing is, because here commutative is not satisfied, so this E plus circle alpha will not be equal to alpha, right? Which is fine. But what we talk about is we say, okay, we at least have we have one type of identity, which is the right identity, right? So this is fine. Inverse also we define in terms of right inverse. So we say alpha plus circle alpha inverse should be equal to E, right? So this implies that alpha minus alpha inverse should be equal to 0, right? So what is such alpha, right? Which means that alpha inverse is just alpha, right? So every element is its own right inverse, right? So these are all properties which are satisfied. So in this way you can prove whether a given operation on a given set, is it a vector space or not, right? Then we have even the scalar multiplication operation. So we are looking at the field um, defined by R, right? So the field here is R. So identity element, so I can choose 1 as the identity element, and because 1 into any alpha is defined as what? Oh, sorry, this is defined as minus alpha though, right? So if I choose minus 1 as my identity, what will happen? Minus 1 dot alpha will be equal to alpha, right? But this doesn't work because the idea is that the multiplicative identity of the field should also be the multiplicative should be the identity of this particular vector space, right? So this is also not satisfied, right? So 1 into alpha is not equal to alpha, it is minus 1 into alpha, so therefore this doesn't work out. Compatibility talks about right, c1 c2. Let's say if I have two numbers c1 c2 dot alpha, is it equal to c1 dot c2 dot alpha, right? Which implies this is just minus c1 c2 alpha by definition. This is c1 dot, this is minus c2 alpha, right? Which implies that minus c1 c2 alpha should be equal to, now this is one vector, this is a scalar, again multiply again do your scalar multiplication operation. So what happens is you will get minus of c1 times minus c2 alpha, right, which is equal to c1 c2 alpha. Now this is not always equal, obviously, so it should be true for all alpha, for all c1, for all c2 and all, right, which is not true. Therefore even the um, compatibility is also not satisfied, right? Then coming to distributive talks about that if I have c dot alpha plus beta should be equal to c dot alpha plus c dot beta, right? So yeah, so this is basically minus c times alpha plus beta. Oh, 1 second, this is alpha plus circle beta, sorry. Yeah, so this becomes minus c times, this is alpha plus circle beta, right? That's the vector operation being defined here. Alpha plus circle beta is basically alpha minus beta, right? So this is alpha minus beta, this is minus c times alpha, right? This is one vector minus c times beta, right? So it's minus c alpha plus c beta, this is minus c alpha plus c beta. So distributive, so dot is distributive over your vector addition operation defined here, right? That is fine. And in distributive we have another this one which talks about the scalar addition being distributive over the vector multiplication, right? So therefore something like this, so c1 plus c2 dot alpha should be equal to c1 dot alpha plus c2 dot alpha, right? This addition is the addition defined on the real number space, right, over the field. This plus is that field addition, so this is fine. This is a scalar, so dot alpha is just minus c1 plus c2 times alpha by definition. This is again minus c1 alpha. This is the vector addition defined, right? So this is plus circle because it's between two vectors. So this is plus circle times minus c2 alpha, right, minus c2 alpha. Now this is a plus circle b, so which is nothing but a minus b in our case. So a then minus b, which is minus c1 alpha plus c2 alpha, and this is minus c1 alpha minus c2 alpha, so which is again not true, right? So distributive may you have two properties, one and two. One is satisfied, two is not satisfied, right? So in this way you can check exactly whether the given operations on the given set is it a vector space or not, right? And we also did this problem too last time, which showed how to prove things like closure and stuff, right? um, yeah. Okay, with this we'll move on to the and then we went to this something called as subspaces, right? Where we talk about subspaces as being a subset of a vector space in some sense, right? And that being a vector space in itself. And then we showed how do you verify whether a given subset is a subspace or not, right? And then we also spoke about some examples of subspaces. So we had this particular problem, which is a bit of which is a bit interesting. So I'll just try to give this an idea on this also. Let me just yeah, this is let's go to, yeah. So this was matrix multiplication. Okay. So one very straightforward idea is that any subspace should have a zero vector in it, right? Because it's a vector space in itself. So what we need to check is whether zero belongs to right, whether the zero vector belongs to this W or not, right? So if you think about it, what are we saying? We're saying that each x1, that is each xi should be zero, right? Uh, is such a vector belonging to W or not, right? But W contains only those vectors which has this property that x1 should be equal to 1 plus x2, right? In this case, the zero vector will not satisfy this condition, right? 0 is not equal to 1 plus 0. So hence, zero vector does not belong to W, which means that W cannot be a vector space in the first place, right? W is not a vector space, and hence it can't be a subspace also, right? That's one way of going about it. The other way is using the theorem that we proved before. That is, if I take, for example, two vectors, alpha and beta, which belong to W, and I should, if I need to check whether alpha plus beta belongs to W or not, right? So if alpha and beta belong to W, that means alpha 1 is 1 plus alpha 2. Similarly, beta 1 is 1 plus beta 2, right? Now here the first element of this particular vector will be alpha 1 plus beta 1, right? Is this equal to 1 plus alpha 2 plus beta 2, right? Which is obviously not right, because when you add these two, what you get is alpha 1 plus beta 1 is 2 plus alpha 2 plus beta 2, right? And hence it's not a subspace, right? Okay. And then we saw something called as the null space of a matrix, which is a important subspace of the vector space of the Fn space, right? And we proved a bunch of things, and then we finally came down to this idea of what does it mean for any subspace to be spanned by a non-empty subset, right? Which basically turned out to be just the linear combination of vectors in S. Now this idea we will use today in trying to understand how to define things like bases and dimensions, right? So moving on, so today's topic is talking about basis and dimension. First, we'll define something called linear dependence, right? So here we have something so let's say we have a vector V, which is a vector space over the field F, and then we have a subset S, which has linearly we say that a subset S is linearly dependent if I have some vectors in S which are distinct, and I have some scalars C1 and to Cn in F, which are not all zero at once, right? That means there exists at least one Ci which is not zero among all I, right? For all I, right? So in that sense, such that this is true, right? That is, if I take the linear combination of these vectors alpha 1 to alpha n with these scalars, right, C1 to Cn, I get the zero vector, right? So this basically tells you that there is at least one Ci which is not zero, right? And if this happens, then we say that these vectors alpha 1 to alpha n are linearly dependent. Okay. And so this is for any set. For example, let's say I define a set like this, right? Let's say I'm looking at R2 space, for example, right, where I have vectors belonging two-dimensional vectors, right? So let's say I'm talking about 1 0, right, and then I have 2 0, and then I have 0 1, right? So I can find scalars like this, right? And let's say it's defined, the v is defined over Rn. Let's say we'll talk about Rn vector space, sorry, R2 in this case, right? So I can find scalars like this, right? I can say 1 times 1 0, or I can take minus 2 times 1 0 plus 2 times 1 times 2 0. This will become basically minus 2 0, right, by scalar multiplication operation. It will become 2 0 against scalar multiplication operation. Now I do the vector addition here, which is 0 0, right, which is the 0 vector of this particular vector space, right? So I'm able to find scalars which are not all 0 at once, right, and hence form the 0 vector. So therefore I say that these two vectors 1 0 and 2 0 are linearly dependent, and therefore the set S becomes a linearly dependent vector set, right? So any vectors if I find which satisfy this property, right, that if I take some linear combination and I get 0 as a result, then that set is basically a linearly dependent set, right? Now, so linearly independent is basically a set which is not linearly dependent. So I cannot find any two vectors in that set which can any vectors in that set which satisfy this property. Okay, so so one example, and we'll go ahead and prove all of this in a while. So one example I could show is, for example, let's say in R2 space itself, I can define the vectors like this: 1 0 and 0 1, right? So any combination of these two, if I take, they will never be 0 unless and until all Ci's are 0, right? So let's say C1 times 1 0 plus C2 times 0 1, right? This will be 0 if and only if all Ci's are 0. For all I, Ci is 0, right? So therefore this is a linearly independent set. Okay, fine. Then we'll come to the consequences of the definition. So so in the way we have defined, let's see this. For example, let's say any set which contains a linearly dependent set is linearly dependent, right? So let's say I have a set L. Okay, let me just use a different set D. Yeah, so set D is linearly dependent set, right? A dependent set of some vectors. Now I will have S, which is a superset of D, right? It contains this particular elements of D also. So I'm saying that since D is linearly dependent, S is also linearly dependent, right? Why is that? So since D is linearly dependent, so let's say it contains some elements alpha 1 to alpha m, right? Again, you can prove this for infinite set also. I'm just proving this for finite sets because it's easier to understand, right? Same proof applies for the infinite sets. So here the idea is that that means what I can do is I can find scalars such that is 0, right? This is true, and there exists some Ci which is non-zero, right? This is what by definition of linearly dependent set, right? Now, since S is a superset of D, right? S is a superset of D. What that means is, so let's say S contains now alpha 1 to alpha n, obviously, and it also contains some beta 1 to beta m, right? Some other vectors in this set S, right? Now what I can do is I can always choose the same Ci's, right, whatever they're here, plus I can choose beta i's, let's say di, some constants di beta I, such that where all di is 0, all di can be 0, right? And in this set I know for a fact that at least one Ci is non-zero, right? So this becomes a linear combination of vectors, right, in which at least one Ci is at least one of the coefficients is non-zero, and this is giving me a 0 vector, right? So hence this set is also a linearly dependent set, right? So the idea is that since D is a linearly dependent set, I can always find a set of numbers, set of scalars in the field F, right? Such that this new set which I'm constructing, or which I have, is also a linearly dependent set. Okay, that's property number one. I mean, consequence number one. Second consequence is any subset of linearly independent set is linearly independent, right? So what I'm saying is, so let's say D or L is a linearly independent set, so alpha 1 to alpha m, alpha n, right? Such that so I can write like this, right? So Ci alpha I equal to 0 implies, double implies, double implies for all I Ci is 0, right? Anyway, the opposite is anyway trivial. This is because of definition of linearly independent set, right? So if I choose any subset of this set, right? So let's say I choose S, which is a subset of L, right? I'm saying that this S will also be linearly independent. Okay, so I mean, so will be linearly independent, right? So let's say I choose some, this S to be alpha 1 to alpha k, right? Alpha 1 to alpha k. Now, so if this set S was linearly dependent, right? If S was linearly dependent, okay, then by above property, I should have that L should be linearly dependent, right? L is linearly dependent. But we said that L is not, so L is basically linearly independent. So therefore, this property holds true, right? So any subset of linearly independent set is going to be a linearly independent set. Then any set which contains a zero vector is linearly dependent. For example, let's say if I have a set, let's say I'll call it Z, which is 0 comma any alpha 1 to alpha n, right? Now what I can do is I can choose, let's say this is a Ci alpha I plus some Z times 0, right? Is 0 such that so where, right, I can choose these Ci's and Z such that all Ci's I can give 0, right, and Z I can use non-zero, right? Now this basically becomes a linear combination of the vectors of Z, right, such that at least one of the coefficients is non-zero, right, but it's still giving me a zero vector, right? So hence any set which contains a zero vector is going to be linearly dependent, right? This is the justification for that. Then any set S of vectors is linearly independent if and only if each finite subset of S is linearly independent, right? This again follows from the property 1 itself. Let's say if any subset is linearly dependent, the above set becomes the superset becomes linearly independent, right? And again the idea that any subset of linearly independent set is linearly independent, right? So if I want to go from, let's say I call this part of the statement as A, this part as B, right? So A will imply B because of property 2, right? Because if a set is independent, right, any subset of it has to be linearly independent. So A implies B from property 2 and B implies A from property 1, or negation of property 1 in some sense, right? Okay, so that's the idea about this linear independence and dependence. Now this will become important when we look at basis, which is what we come to. So what is basis basically? Let's say V is a vector space. Basis is defined as a set of linearly independent set of vectors, right, of V which spans V, right? Now we know what is spanning, right? So I'm saying that basis is a set, is some set, right? We already know what is spanning, spanning subspace of a set, right, which is basically just the set of all linear combinations, right? We saw this in the last lecture. Set of all linear combinations of the elements of this particular set, right? So if this set of linear combinations, right, is basically the vector space, right? So if this turns out to be the vector space itself, right? Then we say that this particular set is the basis for V, right? Uh, this is what the definition tells you. Now, what is the dimension of V? So, dimension of V is said to be the elements in that basis, the number of elements, right? So, let's say the basis contains, for example, 3 elements, right? So, we say that dim V, there is a dimensionality of V is 3. That's the notation of telling dimensionality, right? So, we'll look at some simple examples first. For example, let's say we know for a fact that if F is a field, right, Fn is basically a vector space, right? So now we'll consider vectors like this. That is, alpha 1 is 1 0 and so on, alpha 2 is 0 1 and so on, right? Basically, I'm choosing alpha I such that I have zeros before the ith location, right? So this is the ith location or ith coordinate in some sense, or ith location, right? In this tuple is 1, remaining everything is 0. Remaining everything is 0. Okay. So now I need to, I'm asking the question, is this set alpha 1 to alpha n, right, defined in this way, right, I equal to 1 to n, is this particular set a basis for this particular vector space or not, right? So we need to do two things. One is that we need to say that we need to say that this set is linearly independent, first of all, and we also need, so we have two things, right? One is linearly independent independence of the elements, and second thing is spanning V. So we need these two things. So first we'll go ahead and prove that they're linearly independent. So as you can see, if I take some combination of these vectors and equate to 0, right, by scalar multiplication you can see that C1 alpha 1 will just be C1 and remaining with zeros. C2 alpha 2 will be 0 comma C2 comma remaining all zeros, and so on, and Cn will just be all zeros followed by Cn, right? So now I do the vector addition of these. As you can see that all of the the ith coordinate will be non-zero only for the Ci alpha I product, right? So therefore I get Ci here, right? So here C1, C2 and so on, I get Cn, and this has to be equal to the zero vector. Zero vector is basically all zeros with n zeros tuple, right? So this means, so these two have to be equal. That means each element has to be equal. That means for all I, Ci has to be 0, right? So that means, so what we're saying here is that if this has to be true, this implies that Ci has to be, all Ci have to be 0. That means there doesn't exist any I such that Ci is non-zero. So therefore, so the Ci is 0. So therefore, these alpha 1 to alpha n are linearly independent set, right? Then we'll see whether do they span the vector space or not, right? So spanning in the sense, we need to show that any vector Fn, let's say we have a vector called gamma, right, which has elements gamma 1 to gamma n, and since its a vector space is Fn, each of these gamma i's are basically the elements of the field F, right? So when I look at this gamma 1 alpha 1 and gamma 2 alpha 2, right, so all of these basically is just the vector gamma, right? So that means I'm able to represent any vector gamma as a linear combination of these vectors alpha 1 to alpha n, and here's the speciality is that the coordinates, coefficients which I'm using for the scalar multiplication turn out to be the individual elements of the vector gamma, right? So that means I can say that any vector in Fn is a linear combination of alpha 1 to alpha n, which basically implies that alpha 1 to alpha n spans Fn, and therefore alpha 1 to alpha n, this particular basis is set is a basis for the vector space Fn, right? So any F you choose, we know that Fn is a vector space, right? It is a vector space, and now we know that for any Fn, this particular way of defining these vectors as alpha I, where ith coordinate is 1, remaining all the coordinates are 0, is a basis for this, right? So this basically should bring you to the idea that if F is R, what is alpha 1 to alpha n? They're just the n axis that you have. So in physics you might have heard about all these I, jth, kth unit vectors and so on, right? So all of those ideas come about from here, right? And your 3D space, 2D space, where we basically use as Cartesian coordinate system, right? So all of these basically rely on this idea, right? So where you have a unit vector across each dimension, and that unit vector is defined in this way, right? Where it is one for the direction along which it is needed, and remaining all the coordinates are zero. Next, for example, this is the x-axis. The y, I mean the unit vector along x-axis. The y could be y is basically 0, 1, 0, and z is 0, 0, 1, right? And then you use these x, y, z to define a point in that particular space, right? And you say, okay, any point is basically a linear combination of these three unit vectors, which is exactly what we are doing here, right? So any point in Rn, I mean R3 in this case, is just a linear combination of the unit vectors along the three directions that we have defined. Okay. Anyway, so it's a relation with Cartesian coordinate system. Then we'll come to something called as the yeah. So one more example to drive home the point of this, basis and vector spaces. Um, so let's say we have this vector space V, which is a space of all polynomial functions over the field F, right? That is, let's say I have an element F in the set V, such that f of x equals to c naught c1 x plus cn x power n, right? So this is a polynomial function which takes as input some field F, some scalar in F, and spits out a scalar in F again, right? So this is also a scalar in F, right? So now I'll consider functions like these, right? That is fk of x equals to x power k, right? So now we want to see whether this set is a basis for V or not, right? For this particular vector space or not, right? And here k can be from 0, 1 to until infinity, right? See, because I'm saying it's a set of all polynomial functions. So each polynomial function by default is limited to some degree, but that degree can go to any level. So hence I'm choosing it in this way, and then we'll see whether this set is a basis for V or not. Spanning proof is trivial, right? Because I can obviously represent any such polynomial as a linear combination of these fk of x, which is fine. We need to prove something called as linear independence, right? So we'll use a fourth consequence of the definition, that if for any set, if I can prove that every subset of it, right, every subset of this is linearly independent, right, then I can say that this set will be linearly independent, right? So I'll say choose one subset, let's say f naught to fn, okay, and therefore so I'm looking at this particular equation, right? So that is c naught f naught plus c and fn should be equal to 0, which basically means that c naught f naught of x should be equal to 0, and you substitute what is f naught and fn of x, right, and you get a polynomial equation like this, right? Now this should be, so for this to happen, this should be true for all x, right? Why? Because I'm looking at this particular function as a basis for the set V, right? For the vector space V, regardless of whatever the value of x is, that set I'm checking whether this particular set follows linear independence or not. Now the thing is, this should happen. If this should happen for all x, that means all x should be the roots of this particular equation, right? That is, x belonging to your field, all the elements should be roots of this particular equation, right? Now we know that any polynomial in of degree n has the maximum number of roots to be n, right? So hence this can be true if and only if that's the trivial case, that is c naught to c1 to cn should be equal to 0, right? Which basically means that this subset is linearly independent, which then basically implies that every subset is linearly independent, and therefore we have a linearly independent set, right? So this particular way of defining these functions this particular set is linearly independent. Okay. um, Good enough. Okay. uh, then we'll go to this idea that let's say V is a set of all functions which are infinitely differentiable, right? For example, things like all polynomial functions are obviously a part of this. We also have e power x sort of functions. We have sin x sort of functions and so on, right? Now the thing is, so let's say we have a V set V, which is all these functions, and let's say we'll restrict to R case. Okay. Um, so can you think that if the above set, which is defined in this way, that is f k of x is x power k, will this be a basis for V or not, right? Um, there is an idea which is your Taylor series expansion, right? Taylor series expansion for, let's say, a equal to 0, in some sense it's Maclaurin series, right? Tells that any function f of x can be given, I mean can be seen as an expansion of the power of it, right? So I can say f of 0 plus f dash of 0 times x by 1 factorial plus f double dash of 0 plus x square by, so into x square by 2 factorial, and so on, right? So what am I doing here, right? I'm looking at this f of x, that is any function which belongs to this particular set, right, as a linear combination of these sort of functions, right? So here this is f of 0 into f0 of x, right, which is this one. Then this is f dash of 0 into f1 of x. Then this becomes f double dash of 0 by 2 factorial times f2 of x, right? So basically I'm representing this f of x as a linear combination of all of these vectors, right, which is fk of x, and the coefficients are basically its derivatives at a given power of x divided by the power factorial, right, in this way. So therefore your Taylor series is basically just expanding. We are looking at a function f in a different basis, right? The basis is defined to be these bases, that is each of these x squared and so on, right? So this is the idea of Taylor series. So we saw that even Taylor series sort of concepts can be brought about in this particular vector space linear algebra framework. Okay, good. So this is the examples of some basis and vector spaces. I know how we define about things like a dimension and stuff, right? So in this case, for example, fn, we saw that this is one basis, right? Alpha I equal to 1 to n. So the dimension of this particular vector space dim fn will then be just n, right? Because I found a basis which is having n elements in it, right? Similarly, this particular example that we had, set of all polynomial functions, this is going to be dimension of this V space is just going to be infinity, right? Because my basis is a infinite set, right? Infinite sets. Though it is countable, it is infinite. Okay. Okay, good. So this is the second idea. One example of vector space that we saw last time additionally was this fm cross n, right? That is all the matrices, right, of the order m cross n, right, where each element is belongs to f, right? So so if you think about it, this basically turns out to be one possible basis for this particular vector space is, I can define, let me define it like this. Yeah, so I can define something like a I j, okay, as all zeros, for example, let's say, and only the ijth element, right, is the ijth element is 1, remaining are zeros, right, remaining are zeros. So it is easy to see both the properties that we saw before, right? So one is linear independence, right? Linear independence. So the zero vector in this particular vector space is just going to be a zero matrix, right? So zero, such that everything is zero, uh, and m cross of the order m cross n, right? Now, if I choose C I A I J, C I J A I J, right? Summation I and j going from 1 to infinity, 1 to n, sorry, right, to be equal to 0. Now this means that I have a matrix which looks like this, right? C11, C12, and so on. Again, m cross n. This should be equal to all zeros. Again, m cross n, right? This implies that each of these, Cij has to be 0 for all ij, right? Which means that these matrices which I defined Aij are linearly independent, right? And in the same way, you can see that this basically spans your vector space, right? Again, so it's so trivial, right? So here the vectors are matrices, right? The basis will also be a set of vectors in the particular space, right? Which is basically a set of matrices which are defined like this, right? So this is this particular sort of a set is also a basis for this particular vector space, right? And therefore the dimension of this vector space f m cross n will be the number of elements in this set, right? And here I j go from m, I goes from 1 to m, j goes from 1 to n, so therefore I have m into n, that is m n number of elements, right? So the dimension of this f m cross n vector space is m n, right? Again, very straightforward sort of idea. Okay, so this all is in some sense, yeah, so should be clear. Okay, now we'll go on to some theorems. So first thing is that we're saying that, okay, let V be a vector space which is spanned by a finite set of vectors beta 1 to beta m, right? See, we're saying that we have these set of vectors beta 1 to beta m span V, okay? So beta 1 to beta m, right, span V, okay, which implies so we are not saying anything about that whether these vectors are linearly independent, right? We haven't claimed, we haven't made any claim about them being linearly independent, right? So in case we have something like this, what we are saying is then any independent set of vectors in V, okay? So I choose, let's say, some set of vectors V which is independent and finite, right? If I choose any set of vectors which are independent, then that set has to be finite and cannot contain any more than m elements, right? These are the two conditions that I'm saying, right? So let's say if S is a set of vectors which is a linearly independent set of vectors in V, right? Then I'm saying that S has to be finite, okay? And this is a set, right? So it's finite and it contains no more than m elements, right? So it contains less than or equal to m elements, okay? If this is the claim, so what does it mean, right? It means that I can say that it is sufficient to prove that every subset, okay, having more than m elements is linearly dependent, right? So any subset I choose S, okay, of the set V, let's say, if S has more than m elements, then S is linearly dependent, okay? If I prove this, this is just a consequence of this, right? This implies this in some sense, right? So right, okay, so with this we'll try to prove this idea. So let's say S is a set which is alpha 1 to alpha n, such that n is more than m, and we know that beta 1 to beta n spans V. right? So spanning V in the sense any element in V I can represent as a linear combination of these vectors, right? From the previous subspace classical last theorem which we saw. So that means I can represent all of these vectors alpha 1 to alpha n as some linear combination of these vectors beta 1 to beta m, right? So let those particular combinations be, a11 and a1m and so on, right? And we know that aij has to be from the field f over which the vector space is defined. Now I consider this a particular linear combination of C1, this alpha 1 to alpha n, right? Some C1 and C2 I'm taking, right? So then I expand this alpha j as this, that is ji times beta I, right? Because each alpha j is some linear combination of beta i's. And then I'm just putting this cj inside, which is fine because so this is because why? So this is because your scalar multiplication is what is that? Commutative. No, we just saw this, right? The second property of vector spaces, which is compatibility, right? So this is the compatibility property of scalar multiplication in these vector spaces, right? um, and then basically I have two summations. Both of the summations are finite, so they're finite summations, right? So therefore I can interchange them. Implies interchanging is fine, right? So I interchange them and then look at this particular product, right? So I have this sigma j equal to 1 to n aji cj times beta I, right? Now we have a theory, we have a result in matrix theory. We'll prove that later actually, as part of the idea of looking at matrices as linear transformations. We'll do that later on. So currently the result is this, that we can show that there exist CJs which are not all zero, such that this particular combination, okay, becomes zero for all I, right? So for each I, okay, you have these you have these CJs such that this thing becomes zero, right? Which basically means if this is zero, then 0 times beta I is 0, and therefore you get 0 vector as a result, which is what we are talking about here, right? So this is such that where all Cj is not 0, that means there doesn't exist any Ci which is non-zero, right? So therefore we say that this is linearly dependent, right? So with this we complete the proof, right? So any subset which has more than m elements, okay, those will not be those will be linearly dependent, and hence we can say that any independent set of vectors in V will be finite and contains no more than m elements, right? This becomes important to when you start comparing multiple bases, right? So let's say I have a vector space V which is a finite dimensional vector space, right? Then any two bases of V have the same number of elements, right? So let's say I have okay, so I have two bases, right? So I can choose, let's say, B1 and B2, right? So I will choose, let's say, some alpha 1 to alpha m, say some beta 1 to beta n, right? Now since B2, right, is linearly independent, right, and alpha 1 to alpha m spans V, right, from definition of basis, so n has to be greater than or equal to m. Similarly, I can show that m has to be greater than or equal to n. So the only condition that this satisfies is that m has to be equal to n. Simple and straightforward, right? So, and hence, if you find multiple bases, you need to have them. They will have the same number of elements, which means that the dimensionality of V, you can understand it if you find just one basis also is enough, right? So if you're able to find one basis for any vector space, right, which has, for example, let's say n elements, so dim V is equal to n is fixed by then, right? You need not worry about any other basis having more than n elements because of this particular theorem. Okay. Now let's look at something called as we saw that the zero subspace is a special subspace of all the vector spaces, right? Which exists for all which exists for all vector spaces. So what could be the dimension of this zero subspace, right? Um, so in some sense, if you think about it, um, first of all, the idea is that uh, so this basis, for example, right, um, cannot be the element 0, right? See, zero subspace is such that, right, it is basically just the set 0 with all the properties defined, and this will be a subspace of any vector space, right? Now the only elements in the zero subspace is a set 0, right? Now the 0 set, right, is not a basis. Why? Because we saw that any set which has this element 0 in it cannot be linearly independent, right? Because I can always find some scalar, let's say c, some c, right, dot times 0, which is equal to 0, such that c is not 0, right? There exists c which is not 0, and this becomes true for that c, right? So hence this is not a valid basis, right? So therefore we say that there is no basis at all in some sense, right? So if there is no basis, which means that the basis set is empty, right? Which means that your dimension of V, which is basically the number of elements in the basis set, is 0, right? So this is the idea that the zero subspace has the dimension dimension to be 0, right? So any other subspace in the world, right, will not have dimension V equal to 0, right? It will have at least one dimension. That's the another idea that you can take home from here. Okay. Okay, so we'll shift gears for a bit and we'll look at something else for now. Okay. Um, so we have some ideas on so we expanding this idea of dimensions and some more things about this. So we'll come back to it if time remains. What we'll do now is we'll move to something called linear transformations, and which is the bread and butter of this eigenvectors and eigenspaces sort of a definition, right? Um, defining these linear transformations. So the idea is that let V and W be vector spaces over the field F, right? So we have two vector spaces which are over the same field F. This is important, right? So a linear transformation is basically from the vector space V into W is a function from V into W such that this is true, right? So that is, let's say I have a function T which goes from V to W, right? That means it takes the elements from V and puts them onto W. That's what T is doing, right? And if it satisfies a condition like this, that is T of C alpha plus beta is equals C times T of alpha plus T of beta, where alpha beta belong to V and C is a scalar in field F, right? If this condition holds true, then we say that T is a linear transformation, right? T is a linear transformation. Okay. Now, again, this is will be very familiar in some sense, right? Because when we define linear functions, what we do is we look at whether f of ax plus b is equal to a times f of x plus b and so on, right? So in that same sense, sorry, in that same spirit, we are looking at something like this, right? So okay, so here if you think about it, see, alpha and beta are vectors in V. C times alpha plus beta will be a vector in V, right? T of V projects it onto a vector in W. Okay, C times a vector in W plus vector in W will also be a vector in W because of the fact that C is over the same field, right? So W is also defined over the same field F, right? Since C comes from the same field F, so this also holds true. So this equation is fine in some sense, right? So this same field over v and w is because of this particular property, right? Otherwise this c times will not be defined, well defined. Okay, fine. So with this we'll look at one example. So let f be a field, right, where and v is a set of all polynomial functions from f to f. Again, we saw this just now, in the previous hour, that let's say f of x is such that it's a polynomial function. So I can define it like this: c1 c0 plus c1 x plus cn x bar n. We already saw that. See, given, so we know that f is a field. We know that v is a vector space from multiple different examples that we worked out. We also know that the basis for this particular field is f k of x, such that x, which is defined as x bar k for all k belonging to n. Sorry, not n, w, whole numbers, right? 0, 1 and so on. Okay, yeah. So I will now define a function d, okay, which goes from v to v itself. That is, I'm defining a function which takes elements from this vector space, which it takes element as a function f and spits out another function which is defined in this way, right? So if f is defined in this way, the df function, that is the function obtained after applying the the function d over this f, right, is like this, right? c1 times 2 c2 x and so on, right? So one simple inspection shows that d is doing something called as differentiation, right? Which we are familiar with, right? So because when you differentiate this is what you exactly get, right? So now we are asking, is d a linear transformation, right? So what we need to check is, we need to check something like this, right? We need to check whether d times c f1 plus f2, that is, let's say I have two functions f1 and f2 with, on the field f, right? In the vector f, vector space v, right? So if I apply this transformation on this resultant function, will that be equal to applying the operation c and addition on the resultant functions, that is after applying the transformation d, right? So let's say I define f1 like this: f1 is a naught plus a1 and so on, f2 is b naught plus this one. So we know how to do this, how to look at the c f1 plus f2, right? Because so this plus is basically the vector addition over these two elements, right? And c is a scalar multiplication operation on this particular vector f1, right? So this is defined to be just your scaling and adding of your two resultant elements, which is like this, right? This we have seen already in the example when we looked at how is the set v, which is defined in this way, is it a vector space or not, right? Now d times of this function, right, is basically as defined here. That is, I take the coefficient of x as c1, and then I take the x squared term and I do this and so on. So in the same way, what happens is you will basically get something like this, right? c a1 times b, c a1 plus b1, and 2 times all of this and so on, right? So this is definition of the d applied on this function that we got, that is cf1 plus f2. Similarly, you can look at df1, df2, and you do the same addition and scalar multiplication. You will get the same result, right? So therefore, this and this are the same, right? So therefore, d is a linear transformation, right? You can go ahead and prove this for any general function actually, and then b says that this. You can basically check that whether it's true for all functions or not. Similarly, let v be functions which are like this, that is f goes from r to r, which are continuous. So we will look at a much more broader sort of vector space set, right? And I define this transformation tf in such a way that it's basically just the integration from 0 to x f of t dt, right? You need to prove that whether this is a linear transformation or not. Okay, so the same idea you need to apply, whether that is, you need to look at t times c f1 plus f2, right? Will this be equal to c of t times f1, right, plus t of f2? Okay, so this we need to look at. I'll leave it as a homework for now, and we'll do it if time remains. Okay, now I'll define a special transformation. Let's say I have a matrix A, which is from this f m cross n, right? We know that f is so if f is a field, we know that f m cross n is a vector space over all the matrices defined here, and I'm choosing some matrix A from it, right? I'm choosing some matrix A. Now I'll define a transformation, okay, which is goes from fn to fm, right? So this is also vector space, we know. This is also vector space, we know, right? So what does t take you? T takes an element of this vector space fn. There is some n tuple of this scalars, and maps it onto or maps it onto a tuple in the fm space, right? And the definition is t of x equal to ax. That is basically your matrix multiplication, right? Matrix multiplication. Now you need to show that the t is also a linear transformation, right? Now this is a much easier proof. You can see t times cx plus y, where x comma y belong to fn, right? Fn, and c is some scalar in the field f, right? So this basically by definition becomes a times cx plus y. Now we know that matrix multiplication as such is is distributive in some sense. So you get c times ax plus ay, right? And so ax is basically your t of x, ay is t of y. Hence this holds true, right? Therefore t is a linear transformation, right? So ideally, when you want to prove something like this, what you need to do, exactly speaking, is you need to look at something like this, ty of this one, and then you say, okay, I will look at the ith element here. This becomes a times cx plus y's ith element, okay? And then you say, okay, the ith element of such a matrix multiplication, this particular thing will basically be taking the so ith element will be taking the ith row of a and multiplying that with this particular vector cx plus y vector, right? And 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 then you'll have basically like a summation over j coming here, because you need to take each element wise multiplication of a, right? So okay, let's do it. We'll see how to formally prove such things. So this basically becomes, so the ith element of this particular vector will be taking the ith row of a, right? So this will be all the elements of the ith row. So a, let's say ij, okay? The summation will be over this times cxj plus yj, right? This is the ith element of this particular yeah. So the second, you need not write this one anymore, right? So this is, so ith element is defined in this way, right? Now this I can write it as sigma aij c times xj again here, plus sigma over j again, right? So here j will be what? J will be from 1 to n, right? Because you have m rows and n columns. So we are looking at all the elements of the row. That is, every column you multiply with the corresponding element in this vector cx plus y, right? So this n is basically 1 to n, again 1 to n, 1 to n, aij, yj, right? So this by definition is c times ax, ith element, the ith element of ax, and this is basically ay's ith element, right? So this becomes Correct. So now what happens is each of these, so each of these, I mean, the ith element of this resultant is basically, um, so now what you can say is this is basically c times uh, t of x, right? Ith element, t of y, ith element, right? So now I have mapping from ith element to ith element so this is a vector. This is also a vector. This whole thing is a vector, right? And therefore I can now write as that t of cx plus y is just c times t of x plus t of y, right? So yeah, the thing is you ideally need to prove it in this format, but we make some assumptions, okay, that this is all, I mean, not assumptions, we use these results inherently in when going from such steps from 1 to 2 and so on. Okay. Okay, that's the idea I wanted to show. So this sort of a thing will become very important when we look at eigen values and stuff like that, right? Um, we'll see, how we can connect all of these ideas to matrix multiplication, right? Which basically gets applied in your real world issues, right? Okay. Then yeah. So we have one claim to make here. That is, let's say we have a transformation t which goes from v to w. Then I'm making a claim that t of 0 will be equal to 0. Okay. Now here you need to be a bit careful. What zeros are these, right? What is 0 here? So this is the 0 vector or 0 vector of the vector space V. This is the 0 vector of vector space W, right? Okay, so if you take, for example, this example fn fm, what I'm saying is, if I take the all tuples of 0 such that this I mean the tuple of all zeros, and if I have n such zeros here, this will map me to a tuple of all zeros which are m in number. Okay, so the zero vectors, what they are, you need to be a bit clearer when you're working with like this sort of equations, right? Okay, so we know that it's a linear transformation, so I can say that t of c alpha plus beta is c times t alpha plus t beta, which is fine, right? Now this is true for all alpha beta. It's also true for all scalars. So what I will do is I will choose alpha and beta to be 0 and c to be equal to 1. Okay, so now what happens is I have t of 0 plus 0, scalar multiplication and vector addition. Again you get 1 times t of 0 plus t of 0. So you get t of 0 is so and so. Okay, what is t of 0? Is some vector in W, right? So let's say I call it alpha. So what I'm saying that alpha is equal to alpha plus alpha. Okay, now what I will do is I will let's say I will apply the additive inverse of alpha on both the sides, right? Which basically means alpha minus alpha equals to alpha plus alpha minus alpha. I know alpha minus alpha is 0. Again, so here also I can do this property of associativity and say that this is alpha plus 0, which means 0 equals to alpha, right? So the only t of 0 which can satisfy this equation is that if t of 0 is 0, right? So hence our claim is this, right? So whenever you have a linear transformation, the point is that that linear transformation takes the 0 vector from its domain to the 0 vector in its codomain, right? This is a good thing. Okay. Now we'll prove one simple theorem. Okay, but very powerful in some sense, because this will define. I mean, this in some sense defines how to move from one vector space to another vector space. Okay. So let's say I have a vector space V, which is a finite dimensional vector space over the field F. Okay, so dim V is finite. Okay, now let alpha 1 to alpha n be an ordered basis for V. Okay, that is, I have n elements in the basis, so dim V is actually just n, which is finite. Okay, so ordered basis, in the sense I just have some ordering in the basis. So let's say I choose, I get some basis, right? Alpha 1 to alpha n. I'm just giving them some order in them. Okay, this becomes important when we discuss about coordinates and stuff, but otherwise I think for now we can just assume that this is just ordering on the elements of the basis, which we have. Okay, fine. So this is okay. Then we have some other vector space W, which is over the same field. Fine. Let beta 1 to beta n be any vectors in W. Okay. So what I'm saying is beta 1 to beta n can be any vectors in W, and need not this beta need not span the vector space W. They're not linearly independent. No other assumptions are being made. These are any vectors in W. Then my claim is that there is a unique linear transformation T which goes from V to W such that T of alpha is equal to beta I. Okay, so what I'm saying here is that let's say this is a vector space V is a vector space W. Okay, I have a basis for a V, okay, which is alpha 1 to alpha n, ordered basis, so I'm using this square bracket. Okay, here also I can actually use okay, beta 1 to beta n, let's say some vectors in beta W. Okay, if I want to map these alphas to betas, there is a unique transformation that will allow me to do it. Okay, so now we are looking at so this is the idea, right? Going from one vector space to another vector space, how do you construct such transformations, right? So that is what we're currently looking at, and so we'll see how to prove this. Okay, so now let's say I have a vector alpha in V. Okay, so then by definition of the idea of that basis is that I can define I can find C1 and Cn scalars such that alpha is a linear combination of these vectors in the basis, right? So this is the from the definition of basis, right? Because the basis spans the vector space, right? So any vector can be defined in this format. Now what I'm saying is, let me say, so I will define a transformation T such that T of alpha, okay, T of alpha is C1 beta 1 to Cn beta n, summation of this, right? That is whatever the coefficient was here, I'll take the same coefficient, but instead of multiplying with alpha 1, I will multiply with alpha beta 1. Okay, so see, currently I, I I'm just saying how do I map a vector alpha into a vector in beta, right? Because this is also going to be a vector in beta, right? Because beta 1 and beta n are vectors in W, so their linear combination will also be a vector in W. T alpha should be a vector in W, so I'm defining T such that which goes from V to W, which does this for me, right? It takes any element alpha in V, it finds what are these C1 to Cn. Okay, it finds the respective the what you can say, the multiplication elements of the with respect to the basis alpha 1 to alpha n. Okay, it takes the same elements scalar C1 to Cn and multiplies them with beta 1 to beta n, and then forms your the result of the result of applying this transformation T on this alpha is this particular linear combination. Okay, that's how I'm defining T. So now by definition I can see that T alpha I equal to beta I, correct? Why? Because your T alpha I alpha I basically is just summation, let's say j equal to 1 to n Cj alpha j, such that all Cj are 0 except Ci, where Ci is 1, right? So basically that your the element of the basis, that is alpha I, is just a linear combination, but with all of them being zero except its own coefficient, right? So therefore, when I apply this definition on T alpha, I get beta I, right? By definition of the way I'm making this transformation, right? Now till now we have seen that T is a is some way to map elements from alpha from V to W. Okay, now I need to prove that T is linear, right? Now this is a bit straightforward, so I'll leave it to trying these things out. So what you need to prove is, let's say I have two elements. Okay, we're running out of symbols. Let's say TCA plus B, let's say, where A and B are vectors in V, and to prove that this is equal to C times T of A plus T of B. Okay, or let's do it actually. I think, yeah, let's do this proof also. Okay, yeah. Okay, so yeah, so basically yeah, so A is some this one, right? So that means C A plus B. Okay, I'll just skip a few steps here. So I'll define A as some combination of alpha 1 to alpha n, right? So I'll use that to be A1, for example, let's say, or yeah, A1 times, not A1, confusing. Let's say X1, right? So X1 alpha 1 plus C times X2 alpha 2, and so on. C times Xn alpha n. Right? So I'm saying that A is basically X1 alpha 1 and so on until Xn alpha n. So Xn alpha n, and B is basically again the same basis, right? Alpha 1 to, I mean this one, until Yn alpha n, right? So this becomes, yeah, so this becomes C times X1 plus Y1 times alpha 1, and so on up till C times Xn plus Yn alpha n. Okay, now the way I define this transformation is that if I take a vector in this format, I need to I mean the resultant of applying this transformation is basically just multiplying the same coefficients but with beta, right? This is what I get. So C times Xn plus Yn times beta n. Okay, this is fine. So this is the result of applying this particular thing, right? Now everything follows very straightforward, because Ta plus Tb is basically C times, what will be T of A? It will just be again same x1 beta 1 plus until xn beta n. Okay, plus T of B is going to be y1 beta 1 until yn beta n, right? And you can say that these two are equal, so T is linear, right? So this is fine. Now so what we have proved until now, we have proved that there is some linear transformation, okay, which goes from V to W, fine, and which has this property that T of alpha 1 is equal to beta, T of alpha is equal to beta I. Okay, we still need to prove uniqueness. Okay, so so what I've done is I've basically constructed in this format. Now let's say there is some other transformation. Okay, let's say there's some transformation called U. Okay, which has this property that U of alpha is equal to beta I. Okay, so let's say now I choose any vector alpha, which is a linear combination of T of alpha is that's basically your basis, right? So U of alpha basically becomes, since it's a linear transformation, what is U of alpha telling you? Okay, it is summation, sorry, U of summation I equal, I over Ci alpha, right? Now we know that U is linear transformation, right? So this will become sigma I Ci U of alpha I. What is U of alpha I? Beta I, right? Now this is exactly what T of alpha tells you, right? The way we define T of alpha was exactly in this format, right? Take the coefficients, with respect to your basis, and multiply them with beta I, to get the result of this transformation T of alpha, right? So therefore, if I had any other transformation which does this, it is exactly equal to what T was doing, right? So there is only one such transformation, that is basically T is unique. Okay. Now, why is this important? What this tells you? Okay. Let's look at one example. I should have brought this example. Okay, so let's look at the example. Um, so let's say I have a okay. I want to go from R2 to R3. Okay, fine. And my conditions are this, right? Let's say I want some mapping. Okay. Um, in this format, that yeah, so let's say 0 1. Okay, 1 second. Yeah, so let's say I want to map 0 1 to something like -1 1 2, and 1 0 to 2 1 6, or whatever, like this. Okay, fine. So what I'm saying is that if you want to do this sort of a transformation, okay, the T that you will get, okay, will be unique, right? So the thing is, whatever you put here and here, okay, you will have a unique transformation which does this for you, right? And it is so basically, if I want to go from a lower space to a higher space, let's say from R2 to R3, like this dimension is 2, this dimension is 3, I basically need just two mappings to actually go from the lower to higher dimensional space. And let's say if I want to go from R3 to R2 in some sense, okay, so I need to define at least three such examples, which tells me that okay, I want to go from here to here. So 0 1 0, I can say, okay, go to 1 2 or whatever, right? And then I can say 0 1 0, for this you take me to 1 3 or whatever, right? Or 2 3, right? And then, for example, let's say 0 0 1, sorry, 1 0 0, take me to 0 1, maybe 1 0 0. Yeah. Okay. So okay, so I've shown you examples of the standard basis that we saw, right? The alpha I, such that the ith element is 1 remaining color 0. That's one thing. Any other basis also you can use, but the idea is this, that if you want to go from some dimension, some space which has dimension n to dimension m, let's say, right, you need n such mappings compulsorily, because each of these bases of this n will get mapped to some vector which is in its domain, codomain of t, and then and that this transformation will be unique for all of these guys, right? That's the idea. Fine. um, okay, so that's the idea of this, I mean, the use of this thing called as this theorem. Okay, fine. All right, so now we'll look at okay, now we'll look at one important idea. It's called some subspaces of the vector spaces. Okay, and then we'll leave at a very important idea called the rank nullity theorem. So let's say I have this T, which is a linear transformation from V to W. V and W are vector spaces over the same field F, right? So now I define a set R of T, which is called the range, and it is defined in such a way that any vector W, I'll not use this W. Just give me a moment. Yeah, we'll just stay consistent. Okay, let's say beta, some alpha. Yeah. So what I'm saying is, that this basically a set of all such vectors in W, which I can reach from using T. Okay, that is that there exists some alpha in V such that if I apply this T on this alpha, I will get beta. Okay, so that is which is this simple example, a simple thought process of functions, right? Where we talk about range being all the elements reachable, right? All reachable elements in some sense, right? So reachable elements from the function. Okay, so here also we are saying that, okay, I will choose so R of T basically all the vectors in the codomain W, which I can reach from alpha up by applying T, okay, this is called range. We need to prove that, you can prove that R of T is basically a subspace of W. Okay, so we'll leave the proof for the next class. Okay, and the second special subspace in some sense, it's called null space. We actually saw this null space idea already previously, right? Where we defined for a matrix, right? So here the idea is that the null space of a transformation T is defined as like this. That is, for any vector V in capital V, let's say, if you can if by applying this by applying this transformation T, if you reach the zero vector, right? If you reach the zero vector, this zero vector is, by the way, the zero vector of W, right? So because T of alpha always maps into element of W, right? So this is the zero vector of the vector space W, right? So if this happens, so all such vectors in alpha which on applying T get you to zero. So that particular set is called as null space of T. It's called range of T. Okay, so we're saying that prove that this N of T is a subspace of B. Okay, again we'll see the proof in the next class. Now what I define this rank as basically the dimension of this R of T, right? See, R of T is a subspace, right? R of T is a subspace, right? Which means that hopefully I can define a basis over it. So its dimension, that is the number of elements in this basis, is a dimensionality of R of T. And same way, this is also a subspace, and therefore hopefully I can find a basis for it. And the elements in this basis is a dimensionality of N of T. That's the N of it's called a nullity of T, and this is called a rank of T. So rank of T is the dimensionality of range of T. Nullity is basically the dimensionality of N of T. And we have this famous theorem called as rank nullity theorem, which tells that if I have some linear transformation T which goes from two vector spaces, and suppose that V is finite dimensional, okay, then I can say that the rank plus the nullity of T is equal to dimension of V. Okay, see, I want you to understand here that this dimension of V is something which is very specific to the vector space V, right? You don't need a transformation to define dimensionality. But what we're saying is, if you have some transformation, some linear transformation V to W, if you can find the rank and nullity of that transformation, that will be equal to the dimension of V, right? Dimension of V, to define a dimension of V, you don't need a transformation to do that. What we're saying is, if you have a transformation which operates on V and takes you to W or some space, whatever, some vector space, if you can find the rank and nullity of this T, that will be the dimension of V. Okay, and this is true when V is finite dimensional only. Okay, so we will look at the idea of this rank nullity theorem, and we'll see how to prove this idea. So next class we'll go over some of the proofs that we left here in basis and dimensions. We'll also look at some problems, some interesting problems here, and then we'll finish up the rank nullity theorem proof, look at algebra of linear transformations, and then we'll quickly move to eigenspaces, eigenvectors, and eigenvalues. Okay, where we talk about a special type of a linear transformation, and from there we'll move on to the next idea. Yeah. um, yeah. Okay, so that's it for today's class. I'll see you guys on next Friday, 23rd September. All right.